Hey, I'm Patrick McFadden. A lot of you probably already know me. You probably hear me talk all the time anyway. So I apologize for that really messed up looking screen. Last time I talked to you, I was not, but now I am. I'm chief evangelist now, which is really cool because that's what I like to talk about all the time is Cassandra. The evangelist team is here today. It's me and Al Toby. Some of you may know Al from his talks. He's probably one of the best performance people when it comes to Cassandra. He's around today. Come find us if you want to talk to us. We're here to help you. It's all about community. So this year, we've seen so much community growth, and this is really exciting. We did our summit in San Francisco, over 1,000 people there. I think a lot of you were there, and now we're doing this in Europe. We're just going to keep the love going. So today we're going to be doing a lot of talks, but also we're doing some announcements as well. So one of the announcements we're going to be doing is the DataStax Academy for Apache Cassandra. Yesterday I said I was going to put the link out. Here you go. I apologize for the wall of text here. This, for me, is really exciting because this is where we're going to really start seeing people use Cassandra, I think, effectively. We have online training. It's free. You can go out there and do it. This isn't just a couple of webinars. This isn't just a couple of videos on YouTube. This is a full courseware. And you can sign up for this. Go through it. Mr. Cobley, I'm sorry. Take his class if you're up in class. All right, sorry. I see you going, yeah. So we have a lot of content on there. I was personally involved in this. There were several of us that were in the community that were involved in this. Great content. Please sign up for this. We really want to get a lot of people on there. 100,000 registrations by 2014 is pretty ambitious. So a couple other things, a little housekeeping tonight. After the talks, we're going to be doing a reception, but we're also going to be doing lightning talks. And if you haven't seen the lightning talks here, the summit in San Francisco, they were so much fun, and we have a great lineup for tonight too. So stick around. Don't just take off after 5 o'clock. Plus, you don't want to get on the tube at this time anyway. Just stick around and have a beer. The other thing we're going to be doing tonight is our MVP announcements. We didn't do that earlier this year, so we're going to do it today. And that's really exciting because we really like to recognize people in the community, and MVPs are what it's about. So I think I ran through my list and I almost caught us up on time. So I think I'm going to be done talking. You guys are here to listen to Jonathan talk. He's going to be talking about Cassandra 2.0. Of course, Jonathan is the project chair for Apache Cassandra, CTO for DataStax, and pretty much the man when it comes to Cassandra. So here you go.
Are we good? So I've been working on Cassandra for about 5 years now, and for the first roughly 4 years of that, we've really been focused on 3 core goals of scalability, performance, and availability. And by and large, we really we achieved those goals. We're the best in the industry at these 3 important parts of a scalable database. To add a little color to that, a group of researchers at the University of Toronto benchmarked 4 NoSQL systems, and they used MySQL as kind of a control point as kind of a known quantity to benchmark these systems against each other. And they went through a bunch of different workloads. This one is the reads, writes, and sequential scans. So you've got all 3 request types being mixed in together here. And so you can see that Cassandra is not only increasing linearly as you increase the cluster size, but it's also about 4 times as fast as the runner-up. Now, the one problem with this study that the guys in Toronto did was that it didn't include MongoDB. And so MongoDB is kind of playing in a different part of NoSQL. They're more in the rapid development part than the scalable system part. But in the minds of a lot of people out there, hate NoSQL. I've heard of MongoDB. I want to know how it compares to Cassandra performance-wise. So we actually repeated. DataStax hired a company called Endpoint that works on these kinds of things to repeat the Toronto study with HBase and with MongoDB. And so we again see Cassandra about 4 times faster than HBase, which is the line kind of in the middle there. So it's a reproducible result. That's exactly what the Toronto guys saw. So we felt good that we're doing it right. This is done with both of these benchmarks were done with an open source benchmarking suite called YCSB. It's available on GitHub. So we felt good that we were getting a reproducible result. MongoDB, you can see, it's roughly 20 times slower than Cassandra once you start throwing a lot of data at it. And so that's actually an important caveat, because if you look at the MongoDB site, all their numbers that they give you are from data sets that actually fit 100% in memory. And so, when you start getting into the real world, people don't want to have to get enough RAM to fit their entire data set in memory. You want to fit your hot data in memory, but there's no sense in spending extra money on keeping your cold data in RAM as well. So I actually told the endpoint guys, make sure you benchmark a data set where you have the hot data set fitting in memory, but more cold data than will actually fit in memory. And so when that's why this graph looks very different than the ones you might see where someone did a toy data set and said, hey, MongoDB's fast. Well, it's fast until you get outside of memory, and then things really start going through the floor. These are some experiences that people have had with Cassandra in the field. Speaking to the reliability and availability story, in the bottom center here you have Nathan Milford from Outbrain, lost a data center when Hurricane Sandy hit the east coast of the United States. Cassandra powered through. Cassandra also deals well with small outages, not just really big ones. So Jake Luciani in the lower right, talking about Cassandra dealing with individual disk failures and managing that as well. So Cassandra really gives you reliability in the large as well as in the small, and deals well with both of those. So what we've been focusing on this year then has been really a fourth core value, and really making Cassandra easy to use and bringing that power to people who are interested in using Cassandra and that need a scalable database, but they don't want to live on the bleeding edge. They don't want to necessarily have to dig into the code base to figure out what's going on. So ease of use and developer productivity are really what we want to focus on and what we've been focusing on this year. So that comes in two forms. One is on the right here, we have the Cassandra query language. So up until Cassandra 1.2 in January this year, the main way you accessed Cassandra was with an RPC protocol called Thrift, which was kind of clunky and kind of painful. So we introduced the Cassandra query language, which is basically a subset of SQL. The statements on this slide are legal in both SQL and in CQL. So that's part of ease of use, but another part is making Cassandra more forgiving, making it harder to do the wrong thing. And I'll talk about some of the examples of how we've been working on that as well. As part of bringing out CQL and giving Cassandra a query language, we've also introduced a new native protocol that's native to CQL, that gives you improved performance, that gives you asynchronicity and push notifications out of the box. And so we work on that kind of in parallel with the server piece. And so the Java and .NET drivers, those are both production ready. Python drivers in beta, and we're working on others. There's a talk later today on the Ruby driver for CQL, and the author of that driver will be talking about the low-level details of that. So if you're looking to get your hands dirty with some pretty low-level code, I would definitely recommend checking that out. So one of the important things that we've introduced, we actually support tracing in the old Thrift protocol as well as CQL, but it's so easy to use with CQL that I want to call this out. This actually, for those of you who've been using Cassandra for a while, that you know that this isn't new in 2.0. This was actually introduced in 1.2, but a lot of people don't know about it yet, so I want to keep mentioning it because it's such a powerful tool when you're trying to figure out what's going on under the hood with my Cassandra cluster. So what this does is it's sort of like explain analyze from the PostgreSQL world or something like that, where it actually shows you what's going on when Cassandra executes my query and how long each of those steps take. So here I just have a simple insert statement, nothing fancy, but you can see I've color-coded this, that in the blue at the top, this is the node that the client talks to and gives the request to, and then Cassandra actually has to send that insert off to some other machines. You can see that lower down, and then those other nodes acknowledge the write back to the coordinator, which is what the client is talking to, in blue again, and then it hands back that acknowledgement to the client. So, in a distributed system, obviously you can't just tail your log to see what's going on. You need to assemble pieces from all the different machines that participate in the request, and that's what this does for you in a very nicely packaged, easy to use format. Now, this is one way you can use tracing. And just from CQL shell, you can set tracing on and run your query. You can also trace programmatically, and you can say, I want to trace 0.1% of my requests and save those out. All the traces are saved to a system table. So I want to trace 0.1%, and I'll look through that afterwards and look for slow queries. And then I can say, well, okay, this query was slower than expected. Let's see what actually happened because all those trace events are saved for me. So it's super valuable both in development as well as in production tuning. Another part that we introduced earlier this year that a lot of people don't know about yet is authentication and authorization. So you can enable authentication and Cassandra will make sure that you have the proper credentials to access the cluster when you enable this. So out of the box, in open source Cassandra, we have the password authenticator. So that stores your users and your hashed passwords natively inside the Cassandra cluster. In DataStax Enterprise, we also offer the Kerberos authenticator. So that gives you access to enterprise single sign-on. So as John mentioned earlier, DataStax Enterprise is now free for startups, so definitely something to keep in mind there. And so this is what that looks like in CQL, that I can create users. I can change their passwords as the super user. I can drop them. This is actually something you want to do something like this if you enable authentication. By default, Cassandra just still lets everyone just connect to the cluster and do whatever they want. If you enable authentication, Cassandra creates a default super user whose username is password, whose username is Cassandra, and whose password is Cassandra. So this is kind of the bootstrap user. So what you're supposed to do then is you either create a new super user and drop the existing one, or you change the password on the existing one. That's an important thing to do. We also support authorization, and once I've got these users authenticated, splitting out what data and they're allowed to access and modify. And so I can do that on the key space level, on the table level, and read and modify are separate permissions, so pretty straightforward paradigm. It's what we're familiar with from the relational world. So moving now into the Cassandra 2.0 world. One of the marquee features of Cassandra 2.0 is lightweight transactions. So what we've seen over the last 5 years is that as people deploy Cassandra applications, Cassandra is an eventually consistent system, or tunably consistent if you prefer. And so what that means is there's no way to say, there's no concept of locking. There's no way to say, while I'm doing this operation, nobody else is allowed to touch this data. And that's great for 99% of your application. But it turns out that for a lot of applications, there's a small piece that will need some kind of linearizability, a way to separate and isolate operations from other things going on in the cluster. And so what we saw is that people needed these so badly that they were willing to do unnatural things like integrate zookeeper locking on top of Cassandra to get that. And so this setup, this caused operational problems, this caused development complexity. So we wanted to solve this problem. And so in a nutshell, as an example of the kind of race condition that this solves is, consider creating user accounts where I allow users to specify their own username. If I have two people both asking Cassandra, hey, does username JB Ellis exist? And they both ask that at the same time, and Cassandra says, no, it doesn't exist yet. No, it doesn't exist yet. And then they both go ahead and create and insert that row, then one of them is going to stomp on the other. And so I've basically introduced application level corruption because those operations were not isolated. And Patrick's going to talk in more detail about this in his data modeling talk later on today in this auditorium. But the short version is that lightweight transactions solves this problem for you. So we implement this using a consensus protocol called Paxos. Paxos has a reputation for being difficult to use, difficult to implement. It's actually not that bad. There's a paper called Paxos Made Simple. Most of the complexity in Paxos comes from trying to elect a master that then does most of the Paxos operations, but then if the master fails, you need to do a re-election. And we're not doing that. We're keeping it a fully distributed system with no master, and doing Paxos at a purely peer-to-peer level actually isn't so bad. So this gives us the properties that we're used to with Cassandra, that if a node fails, life goes on. As long as we still have a majority of replicas alive, we can still make progress. So that's the world we want to live in. We don't want to compromise availability to deliver this. Now, the trade-off is that we do compromise on performance. So in particular, we need 4 round trips to do a lightweight transaction versus 1 for a normal update. So, roughly speaking, you're going to have 1/4 of the operations per second than you would with normal updates. So, what the design goal here then is to support that 1% that really needs it, and continue to build the rest of your application using eventual consistency. Now, when people hear that word, eventual consistency, they start getting scared and nervous. And what does eventual mean? Well, eventual means that it's going to be replicated within a handful of milliseconds, as long as nodes aren't going down. So basically the same situation as you're used to. If you've got MySQL master-slave replication set up, same kind of situation. That's actually an eventually consistent system where the slave doesn't get the update for a small amount of time after the master does. An engineer named Christos from Netflix in the United States gave an excellent talk at our San Francisco summit on building applications around eventual consistency and kind of his learning process as he migrated from Oracle to Cassandra, and basically how he learn to appreciate the advantages that it introduces to application design and reliability. So the syntax for lightweight transactions. So we've got two different cases here. We've got on insert and on update. Both of them use a new if clause in CQL. For inserts, it's really simple because all we can do is insert this if it doesn't already exist. So that's super straightforward. So it's just if not exists. On the bottom here, we have an update, and that can actually be a little more complex because I can specify an arbitrary number of columns in my if clause. And so, and they all have to be conjunctioned with and. So there's no or involved here, but I can have as many columns in my if clause as I want. And then I can update the, here I'm updating the same column that I'm checking in the if clause, but that's not required. I can update arbitrary columns as well. In fact, under the hood, I can update any rows that are in the same partition as the one I'm checking. That's not fully exposed in CQL yet, but we're evaluating our syntax options to make that possible. Another new feature in 2.0 is triggers. And so this is fairly, it's straightforward until it's not. And so what I mean by that is on this slide, I have create trigger, very straightforward. But what you see here is I'm giving it a class name. So that's the part that's less straightforward, is that you have to write Java code or something that compiles down to a Java class to implement the trigger. And so the reason is that we have people and companies now that have Cassandra clusters of over 1,000 nodes. So while I said that we've been focusing on ease of use this year, we haven't forgotten about the people who are really pushing the envelope in terms of scalability and performance. And when you have a 1,000 node database, it's actually worth a bit of complexity to get that extra performance from pushing some logic closer to your data. So the trigger allows you to, based on rows being modified, take some action and push a tuple out to your Storm cluster, or read some data from the Cassandra cluster and push it out to some other tables. So at that scale, performance does matter, and people are willing to write some Java code if that's what it takes to get that extra performance. That said, for 99% of the people in this room, we're putting big scary quotes up for triggers and saying, you probably shouldn't use this yet. We know for a fact that we're making changes here in 2.1. It's not going to be backwards compatible. So this is definitely one of those bleeding edge features where if you absolutely need the extra performance, it's available. But we're trying to steer people away from it until we have a better idea of what the use cases are that we're optimizing for and have a friendlier syntax to access that. Another thing that we introduced in 2.0 was triggers. So this is actually is cursors on the native protocol side. So what this allows you to do is not have to worry about manually paging through a large result set. So if I have this timeline table where I have some tweets that I've denormalized into this table, and I want to say, what are all the tweets that my friends have made? If I have thousands of tweets from people I'm following, then I'm going to need to page through it with some syntax like this, where I'm saying, give me the first 100 tweets. Okay, now give me the next 100. And you can see that, since I have a compound primary key here, the logic for give me the next 100 starts to get slightly painful, because I have to say, give me the tweets from the next partition, or give me the tweets from the current partition that I haven't seen yet. And so the more components I have in my compound primary key, the more clustering columns I have, the more clauses that I need in this paging syntax here. So cursors makes that simple. You just say select star from timeline, and Cassandra handles grabbing more rows from you after you've consumed the first 100 or so. This is actually preserves your state across servers. So if the Cassandra node that you're talking to goes down and you have to fail over to a different one, the cursor actually still lets you resume where you left off in your result set. So very cool in that respect. So we have some minor improvements to CQL as well. We added a special case for select distinct. So we still don't support select distinct as a general case, but as a special case, we allow you to say select distinct primary key, or a partition key rather. So that's actually something we can do very efficiently. We don't need to do a sort and merge. We can actually just grab the partition keys from the data files on disk and give those back to you. It's a very performant operation. So we're okay with giving that out as a kind of a baby step there. Create table if not exists. So just syntactic sugar, so you don't need to do a dance of, hey, check if this table exists. If it doesn't exist, then go ahead and create it. Otherwise, don't bother. So just some syntactic sugar there for you. Select as. So we've been introducing some functions into CQL. So it's more important to be able to allow you to create aliases for that. So if I asked for the date of function for a cell, then I can give that a name, or it's any arbitrary function call or column, I can rename that in my result set if I want to. Alter table drop column. This one's a little interesting here. So the history there was that we actually had a drop column in an early version of CQL, but all it did was it removed the metadata for that column definition. So it left your actual data sitting on disk. So for 1.2, we removed drop column entirely. For 2.0, we added it back the right way, which is that when I say drop a column, not only does it drop the metadata, but as my data files get compacted, Cassandra will omit the column that you dropped. So it's not going to go through and start scrubbing your data files and cause a big impact to your cluster, but it will evict that lazily as the compaction happens naturally. So I mentioned that our goals for ease of use were partly on the developer productivity side, but also partly on the operational side and making Cassandra more forgiving operationally. So one of the things that we concentrated on for 2.0 was moving our storage engine internals off of the JVM heap. Now the reason that's important is that I've tried to diagram it here that the amount of memory that you can allocate to the JVM is roughly about 8 gigabytes before you start getting really onerous garbage collection pauses. So modern servers, of course, have a lot more memory than that available. So we want to move our internals out to that native memory where we don't have to worry about garbage collection. And so that means, of course, that we're handling the malloc and free ourselves, but we take care of that, so you don't have to worry about the heap issues so much. So I'm going to give a quick overview of what happens when you read some rows from Cassandra to explain what we've done here. So on a per sstable basis, per data file, what we're going to do when you ask for rows from your users table, first we're going to check a Bloom filter. And so what this is it's a probabilistic set that tells me with high confidence if I don't have any rows for the partition you're asking for. So if the Bloom filter says there are no rows here, then I'm done. If the Bloom filter says there's probably some rows here, then I'll continue on to the partition key cache. And so that's going to say, if I do have a partition here, this is going to tell me where that partition begins in the data file. So if I hit in the cache, then I'm going to go around this dotted line here, around to the left side. I'm going to skip this next part because I had a cache hit. If I had a cache miss, then I go to this next step in the partition summary. And so the partition summary is a sample of my primary key and partition key in the data file. And what that does is it lets me do a binary search against that to see where on disk I should start looking for this partition. So then once I've done that, then I go to the first place on disk. So I've got this dotted line down the middle. On top of the line is in memory. We've stayed in memory so far. This is my first seek to disk, is I'm going to check that partition index that has all of the partition keys indexed in it, and I'm going to do a sequential scan starting at the place that the partition summary gave me, looking for that partition entry. Once I've got that, I'm going to go to the compression offsets table to turn that into where that data block is in a compressed location. So compression is on by default, starting in Cassandra 1.1. What we find is that what you give up in terms of CPU, you make up for in terms of having that much more data cached in RAM. So even in terms of the performance, you get better performance as well as reduced disk space. So that's why it's on by default. You can disable it, but it's on by default. So once we've got the compression offset, then we finally go and we can go read that data from disk. So the three things that we moved into native memory are the Bloom filter, the compression offsets, and the partition summary. So what's critical about these is that all of these structures grow linearly with the amount of data that you have in Cassandra. So you can see how this can cause, it could catch you by surprise when everything's working fine, until now I have 2 terabytes of data instead of 1, and I start hitting large garbage collection pauses as the JVM valiantly struggles to find enough space to carry on because these structures have gotten so large. So moving those into native memory, basically means I don't need to worry about that so much. As long as I have enough RAM proportional to the amount of disk I have, then I'll be in good shape. And that's a problem that most people are in good shape about. Now the last part that I didn't circle here, the partition key cache, that's still on heap, but that's a fixed amount of space. So you tell Cassandra, I want to give the key cache 1 gigabyte, half a gigabyte, and it will limit itself to that and use an LRU policy to evict the oldest entries as you pull in new data. So it works very well with the Cassandra goal of I'll keep my hot data in memory, my cold data on disk. One other thing that we improved on the operations side is a couple improvements to compaction. So one of those is that compaction is always single pass. In 1.2 and earlier, if you had a large enough partition, we would have to do 2 passes on that to compact it because of some details of our data storage format. So we actually changed the format to be able to do a single pass compaction and save you that performance when your partitions get large, which they sometimes do. The other one is that leveled compaction. So for those of you not super into the nitty-gritty of Cassandra operations, LCS stands for leveled compaction strategy. STCS stands for size-tiered compaction strategy. And what those are is that size-tiered compaction strategy is the default compaction. and it's more I/O efficient, but it does a less good job of evicting old data, obsolete data from your data files, and it will tend to give you less good performance on reads than leveled compaction. So leveled compaction is a popular option, but it had some kind of poor behavior under some corner case scenarios, and that's what we're addressing here. So what leveled compaction does is it guarantees that in any level above level 1, we'll only have one data file containing data in a given partition. So if I go and I want to read some rows from a partition, then at most I will have one data file that I need to hit per level, plus any data files containing that partition in level 0, because level 0 is where newly flushed data files appear that haven't been organized into levels yet. So those could potentially contain multiple entries from my partition in level 0. So the problem is that it's actually relatively easy to have a write spike that Cassandra can accept and write to disk faster than compaction can push this out into the levels. So what I end up with is a scenario like this, where now I'm having to check hundreds of SS tables for this partition. So because compaction gets behind, my read performance gets worse. So now I'm doing more I/O on reads, which means there's even less I/O to do compaction, so compaction gets more behind, and you can get into kind of a vicious cycle there. So what we're doing in 2.0 now is when the level 0 compaction falls behind, is we'll actually do size-tiered compaction, which is significantly faster. And so that it's not going to give me, it's not as good as if I had all that data merged into the levels, because I'm still doing those 3 extra reads or however many extra reads in my size-tiered component, but it's a lot better than doing hundreds of extra reads. So this is not a silver bullet that makes leveled compaction a ton faster, that you can just beat the hell out of it with without caring about how leveled compaction is doing. But what this does do is it lets leveled compaction tolerate spikes in the write load and say, okay, I'll just size tier these up. When the write load dies down again, then I'll be able to get back to pushing those out into the levels and catch up. So if you're 100% writing as fast as your cluster can tolerate it, then size-tiered compaction is still really the only option. But if you have the workload where leveled compaction can mostly keep up, but you do have those brief spikes in extra write activity, then this helps out a lot. The last improvement operationally in 2.0 is what we're calling rapid read protection. So what Cassandra does is when you tell it to go do a read, it will send as many requests out to Cassandra replicas as it needs to satisfy the consistency level you're asking for. So if you have 3 replicas and you do a quorum read, it will send out requests to 2 replicas. If you are reading at consistency level 1, it will just send out a single request. So what that implies then is to successfully finish that read, it needs all the replicas it sent requests to actually respond to those requests. And so what you would have then is if a node dies before the failure detector notices and stops sending it requests, then you would have this blue line here that goes down to the bottom. Those are requests that are timing out. They were sent to a replica. The replica died, and then the coordinator waits for those requests. Nothing happens. It sends back to the client, sorry, timeout, failure. So what we're doing in 2.0 now is we introduce this rapid read protection so that the coordinator doesn't just wait until the request times out. What it will do is it will wait until the request is taking longer than most. So by default, starting in 2.0.2, which will be released probably next week, starting in 2.0.2, this is enabled by default at the 99th percentile level. So if a request takes longer than 99% of other requests, then we figure something's probably gone wrong. Maybe that replica died. Maybe it's just ran into maybe it ran into a garbage collection pause. But whatever the reason, whatever's causing it slow, we don't really care why it's slow. What we care about is finishing this request. So I'm going to make a duplicate request, a redundant request to another replica. So I can get that request done before the client timeout expires. And so what you see at the top there are a bunch of different options depending on how aggressive it is. You can see at the top there, one of the lines is 99th percentile that's right next to the no read protection at all. So the line at the bottom there, the orange line there, that's always do a redundant request. So you can see that has an impact on my throughput. When I'm always doing a redundant request, or the next line up from it is 75% of the time, so you can see that there is an impact on throughput. But at 99th percentile, I'm only doing it 1% of the time. The impact on throughput is negligible, and it still saves me from having to fail some requests when I lose a node. So it seems like a good default to have. Another value that might make sense would be taking that down to 90th percentile. So doing extra requests 10% of the time. And the reason you might want to do that is that's going to help out my 99th percentile latency. So I didn't have room here for another slide showing the impact on latency, but this also smooths out the latency curve as well, the latency distribution as well. So if I'm only doing and redundant reads 1% of the time, now that's not going to help my 99th percentile latency. It'll help my 99.9 latency, but not my 99th. So if I bring the read protection down to being more aggressive at 90th percentile, then that will flow into a better latency distribution at the 99th level, which is something that a lot of monitoring people care about. Moving on to 2.1. We're looking at delivering 2.1 in January of 2014. So we've got a pretty good idea of what we're looking to deliver there now. So one of those is user-defined types. So we've kind of started giving you access to nested data with collections in CQL already, and user-defined types takes that to the next level. Because I can create a type like address here that has multiple fields, and then I can use that in a column value or even in a collection value, and those can be nested arbitrarily. So here we have a simple example with just one level of nesting where I've got the addresses inside a map, and then I can pull those out with a fairly simple extension to CQL using this dot notation to access fields within the type. Or I could, the main reason I've done that is so that it fits on my slide here. I could just say select star, still get everything back, but then the wrapping gets ugly. So I pulled out just a few of those fields here. We're also adding collection indexing. And so what this lets me do is just create an index in the middle here, create an index on this set collection that I have, or on a map collection, or whatever kind of collection I have. So up until now, we've only supported index on simple fields, simple column types, primitive column types, and this will extend that. So now I can say select star from songs where blues in tags, and that will use the index to do that efficiently. A thing that we're tackling that's more on the low-level operational side is making our Bloom filters more efficient. more memory efficient in particular. So when I'm doing compaction, this is something that a lot of people don't know about actually, is that when I'm doing compaction, I've got this data file here that I have this Bloom filter that says this is my probabilistic set of partition keys. When I go ahead and merge these two SS tables in compaction, it's possible that there's a lot of overlap in the data that those contain, and I end up with basically the same amount of data that a single one of those source SS tables contained, or it could be that there's no overlap at all, and I end up with all the data still there, but now it's merged into a single data file. And so depending on which of those is happening, I would prefer to size my Bloom filter appropriately, because I need to pre-allocate that before I start doing the merging, just because of how the nature of compaction works. So what we do now is we allocate the Bloom filter pessimistically and say, this is how large it will need to be if there's no overlap at all. And so if it turns out that there is a lot of overlap, then we end up with this Bloom filter that's larger than it needs to be. So what we want to do is we want to size it appropriately. So what we're using in 2.1, is a cardinality estimation technique called hyperloglog. And what that does is it tracks a sampling of the distribution of partition keys in each SS table, and so that lets us calculate to within 5% or so of accuracy of how much overlap there actually is in those SS tables before I actually go ahead and merge them. Now, the interesting thing about this is that we can apply this cardinality estimation to more than just Bloom filters. So I talked briefly about size-tiered compaction. So what we do right now is we look, it's called size-tiered because we look for data files that are of about the same size and say, okay, let's merge you guys together into a larger one. And what cardinality estimation will allow us to do is say, okay, we can actually do better than just say SS tables of about the same size probably overlap. We can actually go ahead and look and say which SS tables actually do overlap and do a smarter compaction based on that. So this is the most hand-wavy of my slides here, because we've got code written for everything else that I've been talking about. This part about the compaction here, we don't have any code written here. We just have big ideas in our bug tracking system. So we're planning on doing this for 2.1, but don't send me hate mail if we have to push that out farther. But it looks really good on paper. Another thing that we're working on that's also kind of at the data file level is increasing the repair efficiency. So this is another place where we have kind of an operation that grows linearly with the amount of data in the system. And so what I mean there is that our repair is highly network efficient, because I'll go through your data files per replica. I'll build a hash tree called a Merkle tree that represents the data in that replica. And I'll compare that Merkle tree with the Merkle tree for the other, my peers in the cluster that also replicate that range of data. And so what I do is I'll compare the root of the tree, and if the roots of the tree are identical, then I know that all the data matches. Everything's good. If the root of the tree is not identical, then I'll look at the left half of the tree, look at the hash at the root of that half. I'll compare the right half of the tree, and wherever those halves don't match, then I'll drill down further into that half. So at each step, I'll cut my tree in half that I'm evaluating until I get to a leaf node that says this is the partition or the set of partitions that is that is missing on one of these replicas, and then I can send that over. So it's very network efficient, but building this tree is not efficient. Building this tree requires a sequential scan across all that data. So as I start to get into the terabyte range of data, that starts to get painful. This is my illustration of as that data set grows, I'm still having to evaluate, sequential scan that whole set to build my tree. So what I want to do, and this part we do have some code written for, it's not finished, but we have it, we have an early version that's being reviewed and fleshed out. What I want to do is, as I've added that extra data, I want to be able to build the tree out of just that new data. I should be able to recognize that, hey, I've already repaired and made sure that all the replicas have the data on the left here. I shouldn't need to repair that again ad infinitum. So I'm just going to build the tree now for this new data. So that's going to be a lot more efficient. So our roadmap for 2.1 I mentioned is in January, and we're looking to continue delivering ease of use both on the improved CQL feature side as well as on the operational side. So how close am I to out of time?
Go about 2 minutes.
I've got 2 minutes. So let's do, we have time for 2 questions if we're fast.
So 2.0 in production soon if we're running 1.2 upgrade?
So the question is, when should I put 2.0 into production? Yeah, I think soon is a good way to look at that. So like I said, 2.0.2 is coming out next week. So I would definitely evaluate that, especially if I have a staging environment. Evaluate 2.0.2 in staging, and I'm in a different position than a lot of people in this room. I would be comfortable with 2.0.2 in production. So for those of you who don't dig into the Cassandra code on a regular basis, I would definitely evaluate that in a staging environment. We're looking at getting it into DataStax Enterprise, hopefully by the end of the year. So yeah, we're going to be evaluating that internally as well.
Adding support for more aggregate functions in CQL, is that, I didn't see that in the 2.1 roadmap, but how far out is that?
The question was about aggregate functions in CQL and what the plan is there. I have mixed feelings about aggregate functions because they tend to be, I mean, you can special case things and pre-compute them the way Akunu does for their analytics. But for the ad hoc aggregation side of things, I'm not 100% sure that's a good fit for what Cassandra's trying to do, because you're by its nature, you're giving it a query that may involve a lot of sequential scans, a lot of sorting, a lot of merging. So it's different than the problem we're solving now for online applications that need to do millions of similar requests per second. So I'm ambivalent about it. That said, there are some Cassandra committers who are pretty gung-ho about doing this. Jake at Blue Mountain Capital is one. Their use case could use this and could get a lot of benefit out of this. So my guess is it will probably happen at some point. I don't know if it's going to happen in the 2.1 timeframe, but there's definitely motivation in the community to make it happen. Thanks for your time, guys, and we do need to break. I will be around. Definitely catch me if you have other questions.
Meet the experts room this afternoon?
I will be at the Meet the Experts room this afternoon, yes.